Hello and welcome everybody to my talk on hierarchical temporal memory. My name is Connor Leahy. I'm a computer science student at TUM, a co-organizer here at KaggleMunich, and I have put way too much on my plate for this talk, so I shouldn't waste time and get right into it. So, on the last episode of Enthusiastic Science Man, I held a talk here at KaggleMunich a couple months ago on limits and weaknesses of deep learning, because I'm a little skeptical about deep learning and where it will lead us in the future and some of the really big problems it's having. And I'm not the only one that thinks that. And I showed this slide, a way forward, where I just briefly mentioned some interesting ideas that are kind of floating around the research space right now. And one I was particularly fond of is called hierarchical temporal memory, invented by Jeff Hawkins and his private research company, Numenta. Now, this is something I'm really passionate about, and it generated a lot of interest last time around. And I hope with this talk to show you a little bit of why I think it's so interesting, and maybe you'll find it interesting too. Alright, so in this talk, I'm going to start with talking about the neuroscience inspiration of HTM. So HTM is very much a neuroscience-inspired approach to machine learning. I'm going to give you a high-level overview of HTM, not really going into details, just the most important concepts. First, I'm going to talk about sparse distributed representations, or SDRs, which are kind of like the underlying data structure of HTM. Then I'm going to talk about the concept of the HTM neuron, which is quite different from how, example, deep learning approaches modeling neurons. Then I'm going to talk about spatial and temporal pooling, which are kind of like the most mature, most functioning part of the learning and inference algorithm. Finally, I'm going to talk a little bit about the benefits of HTM, about the interesting properties it has, and give you some links on where to find more if you're interested. Now, before I really get into this here, I have to give a big disclaimer. HTM is very much incomplete and highly experimental. Don't expect an industry-ready, fully fledged system you can just use right now that has no problems, or even something like a full theory of the brain or anything. No, there are many known unknowns and many unknown unknowns, I'm sure. There is a lot of work to be done, and a lot of work is being done. Just last year, there was some really impressive progress here in HTM related to sensory motor interface I'd love to talk about, but I really don't have the time. And on that topic, it's going to be impossible to go in depth here. There's so much we could talk about, just going to give you a really brief overview. So talk to me later if you're interested in the details. So, humans are kind of amazing. They're like in my top 10 favorite animals for sure. The things they do with their tools and their language and stuff, it's pretty incredible. So it seems like it might be a good first thing to look at if we want to design intelligent machines. And this is where HTM comes in. HTM aims to be a theory of the neocortex. That's the big, wrinkly part of your brain that makes up about 80% by volume. This is a really important part, and something some people think is what makes us humans intelligent like we are. It processes your senses, it creates your speech, your high-level thoughts and planning, stores your memories. It's kind of a big deal. And HTM wants to be kind of have a balance between being biologically constrained to not just be, a new machine learning approach that's 5% better than the last one or anything, but really understand what is the neocortex doing, what is it calculating, how, and why. But it also wants to be computationally useful. It doesn't want to simulate every little ion channel, every little field potential, every protein-protein interaction. It wants to understand on the higher level what algorithms are being calculated and how can we make those work in silico. The real genesis of HTM goes back to the late 70s, when a neuroscientist named Vernon Mountcastle was looking at neocortical tissue. You can imagine if you could take out the neocortex and flatten it out like a sheet, it'd be about the size of a large dinner napkin and about as thick, about 2.5 to 3 millimeters of gray matter. And he was looking at these tissue samples and found something pretty remarkable. No matter where he looked, whether at the part that processes sound, or that processes sight, or that produces speech, or whatever, it all looked remarkably similar. It all had the same kinds of cells, with the same kinds of connections, with the same kind of layered structure. Now, there were some differences. Some parts of the brain, had a little more dense connections, a little more sparse connections, or whatever. But overall, the similarities were pretty striking. So, Mountcastle made an audacious proposal. He proposed that all regions of the neocortex are doing the same thing. In particular, he suggested that there is an organization into cortical columns. So you can imagine that this sheet is composed of these columns stacked next to each other, each of them having an internal circuitry that's almost identical. Now think about this. If this is true, he's saying that there is one algorithm, one single algorithm, repeated over and over in the neocortex that is processing all of your senses, producing all of your speech, all of your thoughts, and storing all of your memories. It's pretty crazy. And it's so crazy, you might think, well, that can't possibly be true. Well, there is some interesting evidence that has been mounting over the last decades that seems to indicate there might be something to this idea. There's quite a lot of anatomical data, showing these regularities in the neocortex and also these cortical columns. I won't really get into details here. But what I think is actually one of the most striking pieces of evidence for this theory is an experiment performed in the late 1990s, where researchers switched the visual and auditory input to the brains of ferrets. So basically, the part of the brain that normally processes sight now received information for sound and vice versa. And surprisingly, the ferrets were neither blind nor deaf. They could see and hear and develop quite normally, in fact. After death, they then looked at the brains and found something even more surprising. They found that the part of the brain that normally processes sight now looked like the part that normally processes sound, and vice versa. This seems to indicate that those differences that are seen in the neocortex might actually just be side effects of this one common learning algorithm and not true differences at all. Another really powerful piece of evidence, I think, is that if you look at the brains of humans and compare it to other mammals, especially like apes and similar, there's no difference. There really isn't. They have the same kinds of structures, the same kinds of cells, same kinds of connectivities. Of course, there's difference in sizes. Larger animals have larger brains and so on. But the only real difference between a human brain and, say, that of a similarly sized ape is the size of our neocortex. Our neocortex is huge, big, bulging, way, way larger than you would expect for our weight and compared to other mammals. But again, that's interesting. It's the size, not the structure. Whether human, ape, or mouse, only mammals have neocortices, by the way, you see the same kinds of cells, the same kind of layered structure, the same kind of connectivity. This seems to imply that the only thing that makes us humans, as intelligent as we are, is just having more neocortex. Which begs the question, could you then make systems more intelligent by just giving them even more neocortex? Quite interesting. Now, HTM starts with one simple proposal, is that the function of the neocortex, the thing it was evolved to do, what it's doing all the time, is predict the future. It takes an input and uses that to try to build a model of the world to better predict what will happen next. That is the core of HTM. Now, I'd like to first take the word here, this hierarchical temporal memory, and kind of pull it apart, kind of explain the parts. And I'll do it in reverse order. So I'm going to start with memory. HTM memorizes input of some kind. All right. Then temporal. HTM always has a sense of time. This is really important. It's a core part of Hawkins' theory. So he says the brain always has time. There's always a before and there's always an after. It learns sequences of inputs. There's no such thing as batch learning or something going on here. The example Hawkins likes to use is that you can't listen to a song all at once. Even if I played all the notes in 1 second, you wouldn't understand it. There has to be pauses. The notes have to come before and after each other. It has to be a temporal stream over time. And he says this is happening everywhere in the brain. The brain needs this concept of time. And finally, hierarchical. That the neocortex is organized in a hierarchical fashion. There's quite some evidence that something like this is going on in the brain. That you have like these low-level parts of the neocortex where information from your senses arrives and is then passed on to higher and higher levels that then kind of work their way towards the front of your head. Where information becomes more and more abstract and complex. Now, we know nowadays that it's not quite this simple, that the hierarchy is kind of complicated. There's information coming in from the sides and information going up and down the hierarchy and stuff like that. I'm not really going into the details right now. So, HTM at its Basis is an online learning sequence memory. It learns sequences of whatever its input is, and then uses those to predict its next input. Some information comes in, it tries to predict what the next time step will be. Pretty simple. Now, there are many more complex functions that the neocortex does in a real brain, like attention and so on. This is a kind of a typical diagram you'd see in a neuroscience textbook of a cortical column. You see some kind of input arriving here from the side that goes into this layer 4 and then it's passed up here and kind of moves around, some kind of output. Already pretty complicated. Well, within HTM, by now we actually currently think that there's probably more like 10 layers or possibly even more. And each of these layers is doing something different, probably calculating some completely different algorithm that contributes to its overall function. For today, we're only going to be talking about the best understood part, which is layer 4. This is the only part I'd say is really well understood. Everything else is, yeah, there's still much to find out. Now, there's been real progress on this. As I said, like I mentioned just last year, there was some real improvement in sensory motor understanding, which may help us understand what layer 3, layer 5, and parts of layer 6 are doing. But I'm not going to talk about that. So for today, everything we're talking about is just applying to layer 4. Again, HTM is incomplete. Okay, so the first concept we need to understand is sparse distributed representations, or SDR. Now this is basically a fancy word for sparse binary matrix. So you have some big matrix of 1s and 0s, and it's sparse. So at any given time, only a small percentage of the values are 1s, usually around like 2%. Now this is also called the data structure of the brain in HTM theory. The idea behind it is that you can visualize it kind of as the on and off state of a bunch of neurons at a given time step. So if you took like a big fiber of neurons and looked at it straight on, the neurons that are currently firing are the 1s and the ones that are not are the 0s. And this kind of sparsity with only a few firing at any given time is definitely something that we do observe in the brain. SDRs are the underlying data structure of everything in HTM. There's no real valued input or anything like that. It's all SDRs. All calculations are performed on these SDRs. So input of some kind always has to be encoded into these SDRs. This is thought to be basically what our sensory organs are doing. Your cochlea or your retina take in some real valued inputs from the environment and then encode it into these sparse neuron firings, which are passed on to the brain. So let's talk a little bit about the neurons. Now you see here several neuron models here, including a real neuron. Now we're going to ignore these for a second here and only focus on the real neuron here. So this is a simplified a diagram of what is called a neocortical pyramidal neuron, which is the most important type of excitatory neuron in the neocortex. Let's look at the most important parts. You see here this kind of like bump thing here, which is called the soma, or the cell body. This is where input from a lower layer, such as a lower layer within the neocortex or a sensory organ arrives on what is called proximal dendrites. This is then integrated in some way and can cause a signal, also called an action potential, which will then move up the axon here towards the higher layer within the neocortex. And also there are these root-like structures here called distal dendrites, which connect within the same layer. So to visualize the information flow here, we have this proximal input, which comes from the lower layer, arriving at the soma, which then causes a signal that can then move upwards along the axon towards a higher layer. Now, the proximal input is the part that actually causes a signal to be created. But on a typical pyramidal neuron, only around 10% of synapses are actually proximal. 90% are what is called distal, within these root structures there, within the same layer. Now, these don't actually cause the cell to fire. Instead, they cause it to go into a kind of a different state. And we're going to talk about that in just a moment, what that means. And also, we used to think that information only flows up one way in the axon, but now we actually know there's also always a kind of apical feedback. The information also flows down the other way. We're going to kind of ignore apical feedback for today, but the rest is very important. So to return to our different models here, now that we understand the real neuron a little bit better, we look at the deep learning neuron and we see there's definitely some similarities. There's this concept here of this proximal input arriving from a lower layer that then comes into this soma-like thing where it's integrated and then sends this kind of signal up the axon. But wait, where is the distal input? It's not there. So a deep learning neuron is literally missing at least 90% of what a real neuron is doing. The HTM neuron does a little bit better here. You see again here this kind of proximal input encoded as an SDR arriving, but you also see here this distal input and also this apical feedback all flowing into the neuron. Now you don't really have to understand exactly what's being calculated here or how it's done or anything, just so you know that there is a much closer resemblance to real neurons. And you're going to see why the input, especially this distal input, is important once we get into temporal pooling. So, okay, we have our neurons, right? Well, what can we do with them? Well, we have the following problem. We want to classify some input, and we want to maintain the sparsity that I talked about. The sparsity in our SDRs is really, really important. It gives us lots of really important properties that we want. And we also want to predict the next input. Well, how can we do this? In HTM, we do this with spatial and temporal pooling. Okay, so the first thing we do is we take the HTM neurons and we organize them into layers of mini columns. Now, this is a really unfortunate words that are used. It comes from neuroscience literature. Mini columns and cortical columns are different things. Cortical columns are the big columns we talked about before with the 10 different layers and whatever. Mini columns are little collections of cells within those layers. So mini columns exist within layer 4, and layer 4 is one of the layers inside of a whole cortical column. Each of these mini columns is connected to some part of the input space, also called the receptive field. All cells within the mini column are connected to the same input, so to speak. And each cell itself has distal connections to some other cells within this layer. So this is roughly how this looks. Each dot represents a cell. You see these columns here of cells kind of stacked next to each other. You have some input arriving into one of these columns. All these cells are getting this input. And you'll see these blue arrows here indicating these distal connections coming from within the same layer. So the first step is what is called spatial pooling. It's pretty simple. At every time step, a mini column's overlap is calculated, which is just how many on bits that column is connected to. Then we just select the top X, the top 20, top 40, however many mini columns that have the highest overlap, and we set those to be on. This gives us a sparsity, because we always have this maximum amount of cells that are on at any given time. So this is what this looks like. At time step 0, we have our cells kind of sitting there, and then at time step 1, some input arrives from below to these different columns, and all those cells are set to on. The output of any given layer at any time step is the state of all of its cells. Off cells are 0, on cells are 1. Now, you might say this is seems kind of redundant. Why do we have these columns when all the cells just fire at the same time? Well, and the reason we need this is for temporal pooling. Because spatial pooling itself has no concept of context. The same cells fire at the same input every time. Not super useful. So let's say we want to teach our network the following sequences. A leads to X leads to B, and C leads to X leads to D. Now let's just say we teach our network this. And now our network sees X. What would we want it to predict? Well, if it saw A before, we would want it to predict B. And if it saw C before, we would want it to predict D. And this is exactly what we can do with temporal pooling. It allowed the network to understand context, to remember previous events. Now, also interesting is you might think, okay, well, what should it predict if it sees X without seeing anything before it? Really, really elegantly, HTM will then predict B and D. This is really intuitive way of representing uncertainty. So how is this done? So all these cells have these distal connections. These are where these get it. This is where this comes in. At any given time step, if a certain threshold of those cells that it has a distal connection to are active, the cell is set to a predictive state. Now, this is a very core part of HTM theory, and there's quite a lot of evidence something like this is also going on in the actual brain. Now, what this does is that if now a mini-column fires, and one or more cells within that mini-column are predictive, only those fire instead of the entire column. If no cells are predictive, like before, all the cells in the mini-column fire. This is also called bursting. So let's look at what this looks like. At our time step number 0, we have our cells, with some of them here being in a predictive state. Then some input arrives, and instead of the entire column firing, only those cells which were predictive now fire and inhibit the other cells within the mini-column. And then some new cells that are distally connected to the active cells go into predictive state as well. And this is exactly our prediction for what the next input would be. So the way you can imagine this is that the cells that actually fire within the mini-column are the ones that define the context. So you have an entire column that represents X. And within that mini-column, you have a cell that encodes X in the context of A, and another one that encodes X in the context of C. This way, the layer can learn context. Okay, so this is just a really quick, really brief overview of some of the most important ideas about HTM. Now you might be wondering, okay, well, what can I use this for in my project? What are the things it can do right now? Well, the truth is, we don't really know. There has been very little experimentation done with HTM compared to a behemoth like deep learning. There's just not been that much things tried. People haven't used this algorithm on too many things, so it's not really sure how good it can do many things. But one thing that is definitely important to note is that HTM is definitely totally not a drop-in replacement for deep learning. There are many things deep learning can do that HTM can't do, and maybe some things HTM can't do that deep learning can't do. But overall, don't put these on the same level. Don't think you can just put it in and do the same things. And HTM mostly just offers really new, interesting ideas that, again, as I've said in the beginning, I think this is something that will work in the future, not really something that will work today. But there still are some really interesting things about HTM. It has a lot of very interesting properties. For one, it is highly fault tolerant and includes something called graceful failure. What this means is that you can delete like 40% of the neurons from an HTM layer and it will mostly work exactly the same. And if you keep deleting neurons, what will happen is the performance of your HTM system will decay proportionally to the amount of neurons deleted instead of failing all at once. It is also very insensitive to hyperparameters. So, like how big your layers are, learning rates, stuff like that. HTM performs over a very wide range of these values, which is something quite unlike deep learning in many cases. It is an online learning algorithm, so you can feed it online data, inference, and learning happen at the same time. And in my opinion, perhaps one of the most interesting parts of HTM is that it has no catastrophic forgetting. Now, catastrophic forgetting is a problem you see in, for example, deep learning, where if you train a deep learning system on a certain data set, and then you train that network on a new data set, it will basically always forget everything it knew about the first data set. This doesn't happen in HTM. In HTM, you can feed it some data stream, it will learn that data stream, and then you can start feeding it a completely new data stream, it will learn that, and then if you switch back to the original data stream, it will instantly start again performing just as well as if nothing happened. Finally, it is also unsupervised and uses only local learning rules. So there's no need for any kind of backpropagation or like full network supervisor, thing like that. You can parallelize everything. There are some things, though, for sure, that you can do right now. These are some things, that I found in literature and stuff that are known to work. Well, obviously, you can use it as a sequence memory if your project would need that. One thing that HTM is already quite good for, and I know actually it performs close to state-of-the-art here, is an anomaly prediction. There's actually a commercial product called Grok that uses it for exactly this. The idea is that when your network learns data, it always tries to predict the next step. And when it can't, it leads to that bursting. So by measuring the amount of bursting, you can tell the anomaly, how unusual or strange a certain event is. So you can feed it, a data stream from your network usage in your data center or heat data from an engine or whatever. and it will be able to predict unusual things happening, or detect them well. And another really interesting thing is there's this company called Cortical.io that uses HTM for text understanding. They built a really big system that is kind of similar to Word2Vec, where it encodes words from the English language into these SDRs and while keeping semantic content. And it can be used for all your typical kind of natural language processing tasks. Now, I really think that HTM is something of the future. You know, it's not something that works today, it's something that will work tomorrow. Really what makes me so interested in HTM, what fascinates me so much, is the potential for the future, the things that might be possible. And the obvious thing is, the obviously big thing, is understanding, you know, the human neocortex, the human brain, which besides, you know, the benefits for understanding intelligence and machine learning, also gives, you know, this huge possibility of understanding us humans even better. And of course, on the far horizon, there is this hope that this may help us get closer towards artificial general intelligence and human level intelligence. A final really interesting thing, I think, is that HTM offers a possibility to design a kind of very, very energy efficient hardware, far beyond what can be done with our current von Neumann architecture. I don't really have time to get into this. I'd love to talk about this. Someone interested, kind of thermodynamics here. But let me just say, our biggest supercomputers, which are considered very inferior to the human brain, take up megawatts of energy, while our human brain takes up 20 watts of energy. Something to think about. Now, if this all made you interested, curious, here's some of the places you should go to find more. The first place, of course, is numenta.org. They have a really great forum there, all their papers up there, and they have a GitHub, where you can also find the NuPic reference implementation for HTM. It has a Python wrapper, you can download it and run it right away. If you're interested in learning more about HTM and theory behind it, I can highly recommend the series HTM School, made by Numenta on YouTube. They have really, really great visualizations of many parts of the algorithm. There's also a book called On Intelligence by Jeff Hawkins, which is somewhat outdated. I think it's around 12 years old now, but it's still really, really good, really interesting. It includes many really interesting and strong predictions about what the brain must be doing, and overall is just a really fun read. It's really inspiring and not too technical, so even lay readers can read it without a problem. I feel that I should give little warning here that he makes some pretty powerful, maybe audacious claims about certain things, such as the weakness of non-biological learning methods, which look a little silly in retrospect after the deep learning revolution, but overall still a really, really good book. Really recommend it. If you're interested in the new kind of sensory motor stuff that's been going on, I can recommend watching the talk by Jeff Hawkins called "Have We Missed Half of What the Neocortex Does?", which you can also find on YouTube. So I know this was very, very short. There's so much more that could be said here, but I hope this was interesting and maybe piqued your curiosity to learn more about HTM. Thank you very much.